the Chemistry in its Element podcast. Curious tales of chemical compounds.
This week, explosively unstable chemistry with Francis Addison.
In 2011, a group of researchers at the University of Munich in Germany announced that they were the first people to synthesize an unlikely molecule. The compound, which we're going to call azidoazide, more on that later, is made up of 2 carbon atoms, no hydrogen, and a staggering 14 nitrogen atoms, making it 89.1% nitrogen by weight and one of the most nitrogen-rich organic compounds ever made. From that description alone, most chemists are going to start wincing. Looking at the chemical structure of azidoazide and examining the extreme inequality in charge distribution between the functional groups, it's little wonder that it has subsequently become known as the most explosive chemical compound ever created. But, as you might expect, the story isn't quite so simple. To start with, the team from the University of Munich weren't the first to ever synthesize azidoazide, although they were the first to correctly identify the structure. In truth, they were beaten to the punch by a solid 5 decades. A patent filed in 1961 records a technique for synthesizing the open form of C2N14, which claimed to have a 4th azide group in place of the tetrazole ring seen in the structure identified in 2011. However, further research in 2013 revealed that at room temperature, the 4th azide rapidly cyclizes to form the tetrazole, meaning that the open form the patent describes doesn't actually exist under the conditions they were using. With such confusion over the structure, it's perhaps unsurprising that finding a name for this compound has proven to be a challenge. Its technical name is the incredibly catchy 1-diazidocarbamoyl 5-azidotetrazole, but while that name might be accurate, most researchers would prefer something shorter. One alternative is isocyanogen tetraazide, which is much easier to say. However, as the name originated from the structure published in 1961, it references a 4th azide group that isn't present at room temperature. Outside of the literature, where the accuracy of naming conventions is less important, many people, including myself, have chosen to adopt the pleasingly poetic, if inaccurate, name suggested by Derek Lowe, azidoazide. So, is this really the most explosive compound ever synthesized? It's possible. The truth is that we can't be entirely sure because no one has ever been able to accurately measure just how sensitive it is without it blowing up in their face. The 2011 paper attempted to perform shock and friction tests, but found even their smallest possible loadings, 0.25 joules in impact and 1 newton in friction, were enough to trigger explosive decomposition. In at least one instance, merely touching the compound with a spatula led to an explosion. Concluding that the material was too sensitive to safely handle, the team simply reported that its decomposition thresholds were well below their readings and left it there. Unfortunately, abandoning stress testing didn't see an end to unintended detonations. While characterizing the molecule's structure, they subjected a small number of crystals to a 150 milliwatt laser inside a Raman spectrometer, only to be surprised when the laser's energy proved sufficient to trigger yet another explosion. Perhaps the most concerning detail about all of this is that one of the papers states, "Compound 2 detonated several times during the Raman measurement." Most people prefer to limit themselves to destroying a single spectrometer per day, but then these are the sorts of risks you take on when working with a compound that is nearly 90% nitrogen. With all of that said, is there any real use for a compound as critically unstable as azidoazide? The 1961 patent suggests the compound might be suitable as a primary detonator, a substance which is used in small quantities to trigger an explosion in more stable secondary explosives that can be handled in bulk. And later investigations have supported that suggestion. The team from Munich calculated that the compound has a detonation velocity around 750 meters per second faster than that of 2,4,6-triazidotriazine, a compound currently being investigated as a possible green alternative to the lead azide commonly used in industry. However, while its abilities may be useful in theory, in practice, azidoazide is just too unstable to handle safely, so it's unlikely to find any practical real-world applications. As regular chemistry columnist Derek Lowe wrote when he named it, "The whole thing is trembling on the verge of not existing at all, and if you are minded to make some yourself, then you are on the verge of not existing at all either."
That was Francis Addison with azidoazide. Next week is our last Chemistry in its Element podcast of 2020, and we'll be taking a look at one of the distinctive flavours of Christmas, cinnamaldehyde. If the name hasn't given it away already, it's the compound that gives cinnamon its flavour and odour. Not only does it take a starring role in some festive foods, but it's also being used as an insecticide, an antimicrobial and anti-corrosion agent, and in a very 2020 twist, it's even being investigated as a potential preventative for COVID-19. Until then, get in touch in the usual ways. You can email chemistryworld@rsc.org or tweet @chemistryworld. Thank you for joining me. I'm Ben Valsler.